Okay, so there's our shaft. Go ahead and bring in cantilever. There we go. Okay, so then we can constrain these. You and let's try that again.
We can join in our lamp and really quiet.
See if I can grab that. That and that. So then if I update that, we should have something that looks similar to that. So I've got it.
This is one shaft with that forward.
Yeah, it's just a shaft with that's basically going to be in a cantilever beam.
Right.
All right, so we can save this.
If you guys are going to visit, you need to go to the open lamp. We've got a lamp going on. You're not going to be able to see the shaft. So that you're not disturbing any of the rest of the students in here. Right.
I did not want to select that. Come on, Catia. Sorry. So we'll go into generative structural analysis. And it looks like I forgot to add a material, so let's go ahead and do that real quick. Let's throw steel on to the cantilever. And yeah, so I just did concentric.
Right. But the end of the line.
Yep. Yeah, you can do an offset. So mine automatically were. Okay, so we've got that. Let's go ahead and change our mesh size real quick. So we'll do a measure from here to here, and it looks like that's 1. So let's just divide that into 3. So let's do like 0.33 and do a proportional sag. And then if we double click on this one, I made the beam steel and I made the rod titanium because that just sounds really cool. Okay, so we'll come in here and we should be able to edit the mesh there. Let's take a look and see how long that is for the diameter. So let's just do that divided by 3. So about let's do about 0.15. That should be pretty close. Okay. So now that we've changed those, we should be able to do this pressure fit using this constraint. And then we'll cantilever. Sorry?
We wanted to give you about 3 elements across. So
yeah, so do the measure tool. If you come in here, you can measure it, how thick it is from like here to here, and that will give you an indication of how big it is. But since I already knew it was 1 inch, I just took that 1 inch and then just divided it by 3. For this one. And then for this one, I measured it across, and it's 1/2 inch across. So I just did 0.5 divided by 3. I estimated it to be like 0.15. So now that we've got that, we go ahead and create the connection. So we'll go ahead and click on the pressure fit connection, grab the coincident constraint, and then for this, we'll make this about 1/8 of an inch overlap. So press OK, and that now has a constraint on it. We can cantilever the beam, so let's throw one of those on. Go to the clamp and grab this face. So it's now cantilevered at that end. And then we can add a load onto this face, and we'll do it to actually, let's do it on this face right here. Do load on this face right here, and we will do it in the negative Z direction. So let's do like negative 10,000. Yeah. Okay. We've got a load there, and then we'll go ahead and put a moment onto our rod face at the top there. And we want it to rotate about the...
Don't put the moment on, let's just solve it and see if it will solve with that.
Okay.
We can come back and add another load.
Okay, so let's see if we can solve this. Looks like it's being very friendly. Okay, so it's solved. We can go ahead and do a von Mises. And you'll notice that the load is putting a significant amount of stress around that. So if we do change our visualization here, let's change this to shading with material. There we go. There we go. So the load worked. We can animate that if we want to. Change the speed.
Go to the top of your bar and put a load in the minus Y direction or something.
This one right here?
The connection or whatever that was added between the two pieces.
It was a pressure fit. So if you do the drop down, this is the default. It's kind of like a blue square. If you do the drop down and go to the second to the last one, it's a pressure fit. So then you'll select the coincident constraint.
Concentric constraint?
Yeah, the concentric constraint. And then you can go ahead and just apply loads. So I cantilevered one end on this end over here. Cantilevered it on this end. And then on this end, I applied a load in the negative Z direction of negative 10,000, since it's made out of steel and titanium. And then I'm going to put another load, this time on the top surface, and we're going to put it in the Y direction, so that we can kind of twist it. So then if we run this again, it shouldn't take too long. We can check our stresses, and now you can see that this thing bends, and that the stresses get distributed through from the rod down to the beam. So if we animate this, you'll see that this thing starts to bend, and as it bends, this stress around that connection point gets really, really big. I didn't put a moment on it. I put a distributed load on the beam itself in the negative Z direction of negative 10,000. And then on the top of the rod, I put a load of 10,000 in the Y direction. In the Y direction, yep. On the top, yep.
What view is that right now? Like what? That's the von Mises, you said?
Yeah, this is the von Mises stresses. If I want to do a...
Well, I'm just curious, because honestly, I can show you my different... You did a clamp at the end of the bar, correct?
Yeah, I clamped it, yeah.
So they're getting stresses up close to back by the clamps instead of just right there, right?
Yeah.
So they're getting lots more. What material is your...
My beam steel.
Is your beam steel? What is your beam?
No. I made mine gold.
Gold?
Yeah, gold.
Okay,
but I did different loads and stuff. But I'm just curious, like,
yeah, his beam is steel, and that's why it's not deflecting very much. Yours is gold, and it's basically butter.
Yeah. If you put those types of loads on gold, that would definitely break it. Yeah, so I did 10,000 down on the beam, which is steel, and then it was negative 10,000 in Z, and then at the top of the beam, or top of the shaft, I put positive 10,000 in the Y direction. Right. So as you put that on there, you can check the displacements. You'll see there's a lot of displacement at the top of the beam, which is what we expect. There's a little bit more displacement down here.
Yeah, I'm not gonna lie. I know you said it like 5 times, but I still didn't catch what the 2 load conditions were. You did a downward force like axially through the.
Yeah. So if I zoom in here, I grabbed this face.
Oh, you got that face as well.
And I did a negative 10,000 in the
And
Z.
you also did the sideways at the top.
And then at the top, I grabbed the face at the top.
That is why.
And I put it in the Y direction. And it doesn't matter which direction you guys do it. I just mostly wanted to show you guys how to set it up. I'm sorry that the last model didn't work so well. I think there's probably a problem with how I set it up. But this should be sufficient for the in-class exercise. So just take a screenshot of this and turn it in. And then when you guys are doing your assemblies, just go ahead and set those up, constrain them using bottom-up constraints, and run your analyses. And if you guys run into problems, I'll do my very best to help you guys kind of overcome those.
Beautiful.
So that's the meshing here. So you can also come in here and you can add moments. So if we go to our loads and get rid of that second distributed force load and put a moment on, we can do a moment on this thing, and we can bend it around our x-axis as well. And if we run that simulation, should be able to animate that, and you can kind of see that it, I guess, oh, my load was like nothing. Hang on one sec. Let's go back to the moment. Yeah, let's do like 10,000. That should actually do something. Yeah, so if we run this again, it's 10,000. Yeah, there you go. So I put it in the x direction, so it's bending about the x-axis. And I probably want to change the scaling amplitude, make it more realistic. But if we animate that, you can kind of see that it twists as our beam bends down.
With the scaling amplitude,
it's this button right here. It's amplification magnitude.
but when it's 1, is that supposed to be like what its actual physical displacement will be? Like, it's only going to move at what it would really move? Or is this some ambiguous scale or just 1?
It's just a scale that it uses. You'll notice if I get even to the maximum, it's not even 1.
Okay. Yeah.
So it's just a way of displaying the results. So I just changed it down to something that looked a little bit more realistic. Okay, so you can see that that rod is getting spun about the x-axis, and while that's occurring, this beam is deflecting in the z direction. Okay. So that's kind of how you set it up. You'll constrain your part. You can use offset constraints, coincident constraints, whatever. You'll make sure that you use a connection property to connect it, and then you'll just go ahead and apply the loads and the forces and your constraints as normal, and you should be able to run it. And then when you're done, of course, you need to generate your report, which is just the little script button with the little stress icon on it. So you'll generate your report. You will then email that to byu471fall@gmail.com, and you'll be done with the assignment. So the intent of this thing is not to like really bog you guys down. So hopefully it's pretty straightforward. So you guys will be able to spend more time on your models, getting those models up to speed, and then the mass properties in the assembly FEA shouldn't take too long. The assembly FEA will kind of motivate you guys to actually create a subassembly in your vehicle. So that way you guys can analyze it. The next 2 labs, we'll be doing motion simulation, and we'll also be doing CFD. And so, again, those aren't intended to be something that will bog you guys down, just kind of give you guys a little bit of extra education, but also buy you guys some time to continue to do your models, finish your topology optimization, finish your FEA. So hopefully those won't be too difficult either. But anyway, I think that's all I had for today. So sorry again that was so difficult, but if you guys do get stuck, let me know, and I'll troubleshoot as best I can. I'm probably going to spend most of today training with Dr. Jensen on what went wrong with my model.